Hello everyone, this is video 1.2 on decimals and negatives. So when we talked in video 1.1 about place values, we talked about how we had our hundreds place, our tens place, and then our ones place. And we said there were other place values that kept going to the left, that kept getting larger. Now, once we start talking about decimals, we're talking about place values that go to the right of the ones place. And so we're going to have a place here for our tenths, our 100ths, our 1,000ths, and so on and so on. And we're going to use this decimal point here to remind us where the ones place is. And so we know that everything to the left of this decimal place is going to be place values that are whole numbers. And so this is my whole number place values. And then everything to the right we know are going to be our decimal place values. Just as important, this idea of grouping still applies. And so we talked about how 10 of these ones would make a 10, and then 10 tens would make a 100. So uh, once we have 10 ones, they become a 10, and so once we have 10 tens, they become 100. And we could see that if we wanted to go the other way, if we want to move to the right, the same thing would apply. We could take a 100 and break it into 10 tens, and then take a 10 and break it into 10 ones. So we could still think of it that way. These place values here still work in the same way. Once I have 10 100ths, they become a tenth. And then once I have 10 tenths, they become a 1. So these groupings of 10 still apply. 10 of one place value become 1 of the next larger place value, and then each place value can break into 10 of the smaller place value. So the idea of grouping and the idea of base 10 still applies. For those of you who sort of know like your etymology, you'll recognize that deci means that we're dealing with things that are in tens. So we know that everything that we're talking about here is in groups of tens. So let's look at a number like 31.5 and how we might model a number like this. So we can see here that we've got three tens using our idea of expanded notation from before. We've got three tens, we've got 1, and then we have 5 tenths. So one way that we could do this would be using our number line like we looked at before. So we've got our 0, here we've got 10, 20, 30, and then we can show 31.5 a little bit past that 30. And if we wanted to break it down and show not just the tens but also the ones, and then within those ones we could look at the tenths within that as well. We could show it in a little bit more detail, and we'll look at a problem like that here in a moment. So we could always use a number line to model this as well. But if we want to do something a little bit more concrete, like the base 10 blocks that we talked about in the previous video, then how do we use base 10 blocks to model a number like this? Because our units we talked about as being our ones. And so unless we're going to take one of those ones blocks and cut it up into 10 little equal sized pieces, there might want to be a better way to do that, and there is. So what I'm going to do is I'm going to use my unit to show my tenths. So I'm going to sort of reassign this place value now. So this is my unit, and it represents a tenth. And so this would be 5 tenths. So now if my unit is a tenth, then that means that my long now is going to represent a 1. So everything is being divided by 10. My unit that was a 1 is now a tenth. My long that was a 10 is now a 1. And so likewise, if I take 10 of these and group them together, then they make 3 flats. So I've got 3 flats that make my 30, my 3 times 10. So these were 100 before. Again, we're dividing these by 10 and making them be worth a 10. It's okay to use base 10 blocks in this way. The grouping of 10 still applies. If we're going to do it this way, we just need to make sure that we're very clear about how these are reassigned. If you just show this picture without any indication that the unit is now a tenth instead of a 1, then this is going to look like 315. This is going to have the decimal point in the wrong place. So make sure that if you're going to use base 10 blocks for this problem, and you're going to see a lot of problems like this, just make sure that you're really clear to the reader what each block means in terms of its place value. I wanted to point out that if for whatever reason we were inclined to do it this way, we could also make this using blocks and then flats and then longs. So I could use 3 of the big blocks here, 1 of these flats, and then so if I had a problem where I had an idea that I'm going to extend this into the hundreds, so I might want to hold off those units for the hundredths place if that's something I know is going to come up later in the problem. So I might be doing a problem like 31.5 plus 2.68. So maybe I want to model this number first, but I know there's going to be a hundredths place coming up later. So in that case, I'm going to want to hold that units place for that. When you hold the units for this hundredths place. Anyway, so I could use these base 10 blocks very flexibly. They don't have to just be ones, tens, hundred, thousands. As long as I'm clear about how I am using them, I can use them very flexibly. So in the previous slide, we talked about using a number line for this, and I want to look at this in a little bit more detail. When we did this problem before, we had our number line, we had our 0, we showed 10, 20, 30, and then we had this little mark here for 31.5. There's nothing wrong with this, but maybe I really want to focus on the 0.5 aspect of this more than the tenths. So drawing it this way, the emphasis is really on this idea of this place value that I'm increasing by 10 plus 10 plus 10. And I can show the 31 and then show the 31.5 and sort of break it down into this place value aspect. But if I really want to focus on the decimal part, I can rescale this number line. And so let's say we're going to make this 31. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is my 32. And the reason I made this 5 a little bit bigger of a tick mark is not because it's going to be the answer, but it just makes it a little bit easier to count. If I'm trying to find 7 or 8, I mean, I always count from the other side and count back from there. But I just find, for me, having this middle tick mark either a little bit longer, a little bit thicker, just a little bit more distinctive, makes it easier to count. And so now from here, I can show that each one of these is a tenth. And so this would be 31.1, 31.2, so on, so on, so on, up to 31.5. So the reason why I'm bringing this up is that I can use this number line model, this linear model, pretty flexibly as well. The way that I scale the lines and the tick marks on the number line allow me to focus on different things. Here, again, like I said, the focus is on the tens, and then here, the focus is on the tenths, is on the decimal. And so I'm really focusing on that decimal point. So let's look at a problem like this where we're going to be zooming in on 2.718. And so this is a pretty common problem in the book. So I wanted to go through an example of this. So one thing that we could do is we can start this. And so 5, then there we go. So we're going to start between 2 and 3. So we're looking for 2.718. Well, we know that that's between 2.7 and 2.8. So we know that this number exists somewhere in between here. Mathematically, we would say it's on that interval. Whatever. It's somewhere between here and here. And so what we're going to do is we're going to zoom in on this. So we're going to open this up, and we're going to open this up. And I'm going to draw another number line below this. And now this is going to go from 2.7 to 2.8. And if you're using graph paper for this, it works out really nice because then you can make the tick marks sort of extend down. And so now here's my tick mark here. Now, you should take a second and kind of ask yourself, like, what this represents, this tick mark right here. So on this number line, we were moving by tenths. Now on this number line, because we've rescaled it, we're moving by hundredths. So this would be 2.71, 2.72, 2.73, up to 2.75. So each time we zoom in, we're breaking this by tenths, and so we're extending out one more decimal place to the right, going from tenths here to hundredths here. You might also think of it as, because my endpoints are in units, then I know that these tick marks, because I've broken this into 10 equal parts, is going to be the next place value to the right. So if this is in units, then this is broken into tenths. If these are separated by a tenth, then these tick marks are in hundreds. So you think of it that way as well. So now my 2.718, where is that going to be? Well, that's somewhere between 2.71 and 2.72. So let's zoom in one more time here. So this is 2.71, and this is 2.72. So here's my 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. And yeah, that's a little short, but it's a math class, not an art class. So this is going to be my 2.715. So there's my midpoint between 2.71 and 2.72. And so now my 2.718, this is 716, 717, 718. This is what I'm looking for right here. And so I could put this inside of here and see that it's a little bit further to the right here, and then put this in here and see it's a little bit further to the left here, and kind of get an idea roughly where this is. But by zooming in, by looking at these smaller intervals, I can focus in on the tenths, the hundredths, and then eventually the thousandths place, and get a pretty clear picture of where this number is. So again, you're going to see some problems like this on the homework. We'll talk about problems like this in class. So I wanted to give you an idea of how we would approach a problem like this. So we need to introduce another set of numbers, and we talked about two sets of numbers in video 1.1. We talked about the counting numbers and the whole numbers. So we're going to extend this out a little bit further into the integers. The integers come up so much that they have their own symbol, and their symbol is a Z, but this diagonal part of the Z you write with two lines. So we call it a double-backed Z. Has these two parts there, and we'll look at other number sets eventually that have the same sort of like double line aspect to them. YZ for integers, the German word Z-A-H-L-E-N, the German word for integer starts with a Z, and so that's where the Z comes from for this. So let's put this in context of the other number sets that we've looked at. So we had our counting numbers. And so my counting numbers were 1, 2, 3, 4, 5, so on and so on. And you'll notice this gap here. There's a reason for that. Then we also introduced our whole numbers, which were 0, 1, 2, 3, and so on and so on. And so now we have our integers, and now my integers are going to include all of these, but also -1, -2, -3, so on and so on. Now, I wanted to put these in this way so we can kind of see a little bit of a comparison here. Is there a smallest counting number? Well, yes, the 1 would be the smallest counting number here. And is there a smallest whole number? Well, the 0 is the smallest whole number. Is there a smallest integer? Well, this is the first case that we've seen where we've got the dots going to the left also. So no, there's not a smallest integer, just like there's not a largest integer. This is going to keep going to the right. It's going to keep increasing and keep going to the left, keep decreasing. So think about that as well, that this set doesn't have a largest element or a smallest element. I also want you to be really, really careful, and we mentioned this in the previous slides where these were related, that people use these two terms interchangeably and really shouldn't. We can extend this now even further, that sometimes people use these three terms interchangeably, and they absolutely shouldn't, because you can see that they're very different things. Now, is every whole number an integer? Well, yes, we can see that every whole number that we have here is included in the set of integers. But is every integer a whole number? No, because my negative integers here, my negative integers, are not included in this set. So just be very, very careful with using these terms. Make sure that you don't use them interchangeably. They mean very different things. We should talk a little bit about this idea of absolute value. I'm sure most of you have heard or seen this before. My absolute value is simply my distance from zero. And usually we talk about a number line in order to model this. So let's look at, say, we have a number line here. We've got 1, 2, and 3. And so the absolute value of 3 is going to be this distance from 0. And so we write this with these two bars, these two little vertical bars. And so that this lets me know that the absolute value of 3, and then I know that this equals 3. Now, if we go the other way, 1, 2, 3, so we go back to -3. So then the absolute value of -3 is also going to be 3. A distance is always going to be non-negative, right? So we're never going to have a negative distance. I don't drive 20 miles to work and then -20 miles back home. It doesn't work that way. We could talk about some cases in mathematics where that is the case, but it's not this case, where that doesn't apply to absolute value, where the distances can have direction to them. If you've taken a physics course, maybe you've seen something like that, but that's nothing to do with here. So this distance is always going to be some non-negative. And you might be wondering, well, why is he saying non-negative? Why not just a positive? Well, because the case of 0. So the absolute value of 0 is 0. And as you remember from before, we don't really think of 0 as being a positive or a negative. It's at that boundary between positive and negative. So I can't really say that all these distances are positive. If I really want to be careful about it, I should say that all these distances are non-negative, allowing for the absolute value of 0. The absolute value of 0 is also a special case because every other absolute value has two possibilities to it. So there are two numbers that have an absolute value of 3, +3 and -3. There are two numbers that have an absolute value of 5, +5 and -5. So on and so on and so on. But 0, there's only one case. There's not two numbers with an absolute value of 0. There's only one. And you might be able to sort of tell from this, the extension of this, how many numbers would have an absolute value of, say, -6. Well, none, because again, it can't be a negative number. It has to be a non-negative. So two numbers will have a positive absolute value. only one number will have a 0 absolute value, and then no numbers will have a negative absolute value. So I want you to think about at the end here. I want you to think about numbers that have these absolute values. So can you find a number that has an absolute value of 12.04? Can you find another number? And then can you find a third number? And then why or why not can you find the first, second, or third? So I'll leave this problem open to something for you to think about. And then if we have any questions about this problem, we talk about it in class. All right, thanks.